What up, everybody? Welcome to another episode of Ask Paul. My name is Paul Abernathy, your host. As always, welcome to the podcast where we answer your questions to the National Electrical Code. Of course, if you want to submit your questions for review and possibly for use on an upcoming podcast, then all you got to do is go over to paulabernathy.com and put in your name, email address, and ask your question. And click that button and you submit it, and we will get it, and I'll either respond in an email or, if selected, will be used on an upcoming episode, much like today's episode of Let's Ask Paul. Of course, you can listen to all of these podcasts at one convenient location over at paulabernathy.com, right from the website if you want to listen. Any browser on your device will get you there. Of course, you can also listen to all these on Spreaker, Spotify, iTunes, Apple Podcasts, Google Podcasts, whatever. Just search for the Ask Paul podcast on all of your favorite listening devices. In all of those podcast platforms, you can find us and listen from there. Okay, on today's episode, and I should say, all of these shows are sponsored by Electrical Code Academy Incorporated, the premier educational provider for learning the National Electrical Code. So if you want to get a better understanding of the NEC, then you want to go over to electricalcodeacademy.net. Of course, we have many domains. All roads lead back to the same place, whether it's the fasttracksystem.com, whether it's masterthenec.com, .net, any of them, ultimately will take you to Electrical Code Academy Incorporated, and that's where you can get your educational knowledge on. All right. If you're looking for any swag or any clothing or anything for electricians to promote the pride of being an electrician, then check out electricianpride.com as well. That is our portal for all of our goods and merchandise. So check it out, electricianpride.com, for that information as well. All right. So in today's episode, we're going to be answering a question that was submitted through the portal. And it's ask a question. It says, Paul, can you please explain Table 450.3b for overcurrent protection for transformers and explain how it differs from the protection of the conductors supplying those transformers? Thanks in advance. Okay, great topic. Talking about transformers. Before I get too deep into the transformers and talking about what 450.3b is all about, it's important for me to remind you that we do have an extensive series on transformers, whether it's the secondary conductor rules, the length, 10-foot, 25-foot secondary conductor rule, all those type of things. We do have that covered in another set of videos that are available from our members only area on our website. So you have to do a monthly subscription to get access to them. But again, it's monthly, and you can cancel at any time unless you want to be one of our annual subscribers, and you're basically going to do an annual subscription. It works out about the same. The choice is yours. But if you want to go month to month, that's perfectly fine. If you want to go a month and get all the goodness that you need and you want to cancel, go for it. That's totally up to you. So check that out over on our website. Again, electricalcodeacademy.net, .com, .org. It all doesn't matter. All goes to the same place. All right, so when we're talking about this question, the question is very specific to the table, right? 450.3b, which is overcurrent protection. Now, it is overcurrent protection for the transformer. And I think that's what tends to get people lost, or they get confused and, not understanding what's going on. And you have to remember that you basically have to take into consideration that we have conductors that are going to be used in the primary side, and we have secondary conductors that are going to be used on the secondary side of a transformer. They have to be protected at their ampacity. Now, there are rules that you can follow with the secondary conductor rules in 240.21c for secondary conductors. We have rules in 240.21b if I'm happen to be tapping a feeder to supply a transformer. So we have all these rules we have to follow, and we go into these in our transformer series. But this question today is specifically talking about the table. And a lot of people get confused with this because this is purely only, and it's funny because I had one of my students contact me the other day, and it wasn't from the same person that submitted this question. Because this question was submitted, I guess, weeks ago, and I'm just now catching up to it. they had the same question, right? Where do you draw the line between the conductors and the primary and secondary conductors, and where you draw the line about the use of this table and what 450.3b is all about? And this is a maximum value table for protecting a transformer by telling you how to size the overcurrent protection device, right? So that's all this table is dealing with. You still have to understand your rules for that primary conductors on the primary side. As always, it has to be able to handle 100% of the non-continuous loads. It has to be able to handle 125% of the continuous loads. More often than not, you're going to have, if you know that your load is going to have some continuous loads in it, then you're better off going on and sizing the primary, making sure that you are taking 125% of your continuous and 100% of your non. So most people just keep it simple. I'm just telling you how it is. Most people just keep it simple and just take whatever the calculated value is of the line current of the transformer. They take it at 125%, and that's what they go with, right? But I want you to understand that really the conductors are sized as they would anywhere else. It is based on 125% of the continuous and 100% of the non-continuous. It's just the majority of the time in the field, in working, people just go, you know what, the 125 is the worst case scenario, so I'll just take it and size conductors at 125%, and then we'll just go with it. So a lot of times you'll see educators will tell you that it's a continuously loaded transformer because we're wanting to make it simple for you to say, okay, well, primary conductors have to be at 125% of the line current value. And the secondary conductors are based on, they can't be less than whatever the device is or whatever the overcurrent is that they're terminating into. And then you have the different rules that you have to follow, whereas you can't use a next size up rule for secondary conductors. And all that follows the rules in 240.21c. Most notably, a good example of this would be C2 for the 10-foot rule. So if you want to know how all of that works with some really good illustrations, I encourage you to go get at least 1 month subscription to our program and watch those transformer videos. And while you're in there, going and watch the 8-part series on swimming pools. It's one of the best out there with me and Vincent Delacroix. He's an amazing dude. He works for Siemens. He's a super nice guy too. And he serves on code panel 17 with me. It's a great dude. So you want to check that out. That's part of it. That's worth the price alone. You know, that's worth the annual subscription, to be honest with you. I think it's $120 for annual. Dude, that video is worth more than $120 just to teach you what you need to know. And plus there's hundreds of other ones in there and other podcasts that are exclusive. Check it out. Okay. So that's the last commercial I'm going to do on that. But the point being is there are other rules that you have to follow. But to answer this question that was submitted, we're going to specifically talk about the overcurrent protection for protecting transformers in 450.3b. That's our focus today. Not so much the conductor sizing. Now, for craps and giggles, we might size a primary and secondary just for something simple like a 10-foot tap rule, just to give you context. But at the end of the day, all we're doing right now is talking about protection of the transformer. That's it. That's all we're focusing on. So in your code book, if you were to go to the actual code language in 450.3b, what you're going to read is, it's very short, very sweet. It says, overcurrent protection shall be provided in accordance with table 450.3b. And this is dealing with transformers that are rated 1,000 volts nominal or less, which is probably the lion's share of what you folks are going to be working with, right? It's a whole different table if you're dealing with over 1,000 volts. Works the same way, okay, but a little more tedious in how you look at the table. But we're going to focus on 1,000 volts nominal or less. Why? Because in the question that was submitted to me, the reference was to 450.3b, and that is obviously dealing with 1,000 volts or less. So that's what we're going to do. So we're going to jump down to the table and kind of give you the lay of the land. Now, of course, this is a podcast, so I'm going to do my best to paint you a mental picture because it is a podcast, obviously. Hopefully, you're following along in your code book. But if you're cruising down the road or you're on the job site, I get it. So I'm going to try to paint you this picture. So here's what the table is labeled. It says table 450.3b, it's the maximum rating or setting. So maximum rating or maximum setting of an overcurrent protection for transformers 1,000 volts or less. And of course, it's in parentheses says as a percentage of the transformer rated current. So we have to calculate that out. We refer to that as line current, but we're looking at what the values are that this transformer, depending on what the kVA is, what is its rating, okay, in current. So we're going to have to do that. So there is a little bit of math involved today. Not a lot, but a little bit. Pretty simple math, okay? Well, we'll look at that. Now, if you look at this table, for those that are just trying to draw you a mental picture, it's broken down into primary protection and secondary protection. Now, let me start by saying that primary protection to that transformer is always going to be present. Maybe in a different percentage value, but it's always present. You don't always need secondary protection for the transformer, but those secondary conductors will require protection. And if they terminate into a device or an overcurrent device, saying the 10-foot tap rule, let's say, or shouldn't say tap rule, the 10-foot secondary conductor rules under 240.24c, then if you follow those rules, then you have to make sure you protect those conductors. And those conductors can't be rated any less than the rating of the device or the overcurrent device to which they terminate into. So it can't be less. And you can't use an excise up rule. Now, I told you I wasn't going to talk about conductors, so I'm just giving you that only in a sense to tell you that you have choices here. You always have primary protection for a transformer, but you may not have secondary protection. However, if you choose in your installation, in your design, and you do want to utilize the up to 250% for primary protection, then you are required to have secondary protection. And it can go up to 125%. Okay? That's what we're talking about. So I'm going to break these down. So if you look at the table, you'll notice that it says protection method, and it's primary only. And that means primary protection on the primary side of the transformer. And then you have primary and secondary protection, where that is applicable. Most of the people, be honest with you, most of the people follow the primary only protection, but they ultimately end up, don't exceed 125% of the primary. So it doesn't matter. In the secondaries, the conductors are going to be protected because of the device they terminate into. And the secondary winding doesn't have to be protected because it's protected by the primary because you're not exceeding 125%. In the event that you might exceed that 125 on the primary, allows you up to 250%. Doesn't have to be all the way to 250. Could be 150%. Could be 175% of the line current. That's totally up to you as a design professional. That's up to you. But the maximum is 250. Okay? Now, this maybe comes into play a lot of times when you have multiple transformers being supplied and you have a single primary protection. When that comes up to a situation, then you could have an issue where because of the inrush, you need to be up as high as at 250%. And the key with that is if you choose that, then the secondary protection is required and it can't exceed 125%. And there is a note there. We'll talk about those in a second. But that's the general premise behind what we're doing, okay? All right, so if you look at this table, remembering that this is primary only protection, if it's 9 amperes or more, and it's primary only protection, it says you can go up to 125%. Now, if you go up to 125%, again, of the current rating of the transformer, and we'll have to calculate that out, then the maximum is 125. But if that doesn't correspond with an overcurrent device, you'll notice that it's a note 1 there. And the note 1 is saying, you know what? If that calculation you did up to 125% of this line side current for this transformer, if it doesn't correspond with a breaker that's in 240.6a, then I'm going to let you, as long as it's a fuse or non-adjustable circuit breaker, I'm going to let you go up to the next available standard size in that list, right? So that allows you to jump to the next size. And that's okay for primary only protection. It's going to let you do that, and you don't need any secondary winding protection. You follow these rules. You follow the notes. Now, if you're dealing with the calculation of the line current on a smaller transformer, let's say that is less than 9 amperes or even less than 2 amperes, then you see you have other percentages here, 167 and 300%. Those are maximums. There is no note 1. There is no next size up. You can't exceed 167% and you can't exceed 300%, so you're going to have to move. If it's not magically falls right on the rating of a device, then you're going to have to go down to the next available size. Because if you were to move up here with no note, then you would be exceeding the percentage that's given in the table. So only the ones with the note 1 is going to allow you to go up. And it's only going to be the ones that are associated with 125% values. So you'll notice there's no note 1 for that 250%. It's only next to where you see the 125% that you have this note 1. Okay, so primary protection, if it's 9 currents or more, 125% is your max. Unless it doesn't correspond, then you can use note 1. If it's less than 9, it's 167%. And we'll look at an example in a minute. And then if it's less than 2, then you can go up to 300%. But you can't exceed that with the protection. And there's no notes there. Now, the secondary protection is not required, but it might be necessary. And the reason I say that is, no, you don't have any secondary protection for that winding, the secondary winding. But if that secondary conductors are supplying a panel, and the panel's rated, I'm just throwing a number here, it's rated 200 amperes, then those secondary conductors have to be rated equal to or greater than the rating of the device or the terminals to which, or the overcurrent device to which it connects. So those conductors would have to be at least rated 200 amperes. You with me? There's no next size up rule on that. It says that right in the language of 240.21 for those secondaries. Okay, C, it tells you you cannot use the next size up rule. So they have to be equal to. So we're just talking 10-foot tap rule. Excuse me, I keep saying tap. The 10-foot secondary rule, then that's what we've got. We can't be less than the rating of whatever the device is that we're terminating into. So it kind of dictates itself, right? Assuming that that panel's been calculated out to handle the load and everything's been done right and you know what size panel, that handles the load that's going to be supplied by that secondary, okay? So each thing works kind of in a little piece. But as far as the transformer is concerned, if you're not exceeding 125%, and even if you're utilizing note 1 on the primary protection for the transformer, that's upstream of the transformer, then I really don't need any protection for the transformer on the secondary side. That's for the transformer. But more often than not, you will have protection to the panel that those conductors go into. So in theory, you're going to have some level of protection. Okay? Now, the protection is probably going to be more overload driven since all that load is on the load side of whatever the device is those secondary conductors connected to. But in that scenario, you're still going to protect those conductors, right? But the primary is going to protect the secondary winding, and it's okay. It's fine. Now, when you have primary and secondary protection, where it may be required by some design, or you want to go above that 125% up to the 250, then it's going to require that secondary protection of that winding. Now, there's some exceptions to that rule in 240.21C1, specific types of classes, of voltage class and application. That's a very limited application, by the way. So we're not going to get into that. We do talk about it in Transformer series, but there is occasion where the primary does protect the secondary. And so, it can utilize that. But we're not talking about that example today. It's too hard to convey that in a podcast. And if you want to do that, do your own podcast and send me a link. I'm more than happy to listen. I love podcasts. Okay. Now, if we're doing primary and secondary protection, obviously, if it's 9 amps or more, it can go up to 250%. Note 3 just talks about a specific type of transformer, which is equipped with a coordinated thermal overload protection, and usually it's installed and provided by the manufacturer of that transformer. It's a high end, and it allows you to go as much as 6 times the current rating of that transformer if it's not more than 6% impedance, or 4 times the rating of that transformer When it is more than 6, but not more than 10 of impedance, and that'd be a rather high impedance of a transformer, by the way, creating it very, not as efficient, if you will. But it does allow you to ignore that 250 and go up to as much as 6 times the rating or 4 times the rating, depending on what the impedance is, which could exceed the 250. And it's kind of like the Note 1. That is okay, as long as Note 3 is applicable to your installation. Most transformers, unless they're really big and then they get really expensive, are not going to have any type of coordinated thermal overload protection built in by the manufacturer. If not, transformers are expensive in general, but you're going to know it if it has all that enhanced thermal overload protection in it. And then if that's the case, you're probably going to get directions from the manufacturer, and it's all based on the actual impedance of that transformer. Other than that, you just ignore Note 3. You know what I'm saying? So primary and secondary protection, the max is 250. Now, one of the questions that people ask me is, on an exam, you just go to the max. Because you're allowed to go to the max, you just go to the max, 250%. Exam purposes. In the real world, nobody is going to go to the 250 unless, for example, that overcurrent protection is supplying multiple transformers and you have multiple potential for inrush, and that 250 accounts for that. In the real world, most people are not going to do that. Why? Because if I go up to 250% of that primary protection, then my conductors that are on the primary side have to also be adequately sized for that 250%. And nobody wants to do that. But if you do use that option, then it does need to be sized at up to, and it can't exceed 250%. Okay? And we'll talk about that a little more as we move further into this, but I'm just wanting you to put these things in your mind. Okay? So, you see that 250% is consistent for whether it's less than 9 amps or less than 2 amps. It's 250, 250, 250. The primary protection, if you're going to go up to 250% or utilize this allowance, then the secondary protection can also be sized up to 125%, or if it's less than 9 amps, up to 167%. And you notice there's no Note 1 after that one where it is less than 9. So 167 is your max threshold. That's it. You do have the 125% Note 1. If you do that math and you want to go up to the maximum size for that secondary protection, then you can exceed 125%. But if it doesn't correspond, you are allowed to go up to the next standard size overcurrent device. Again, you find all those in 240.6a, and we're probably by now very familiar with how that works. We do that with conductors and all that type of stuff. So, being said, this table is nothing but protection for transformers. Now, looking at the notes, I kind of explained what Note 3 was. You have Note 1. Note 1 is the one that tells you, hey, if it's 125% of the currents and you're using this, knowing that you could do all this at 100%. Now, people lose sight of that. This is a maximum. If I don't want to do any of these percentages, I could do the primary protection at 100% or whatever the rated current is of the transformer, and the same as secondary. I could do that if I want. But you have certain inrushes and things like that, so they allow you to go up to a certain percentage and still consider the transformer protected. That's fine. In some cases, the engineer might go to 150% or 175%. Just remember that when they exceed the 125 and they're going up, that would kick in the requirement for having primary and secondary protection for that transformer. And the secondary protection for that transformer will be protected by the overcurrent device that those secondary conductors terminate into. So, and there are rules for sizing that you have to be aware of, okay? Which we're not going to go in details today because this was just about the overcurrent protection. So be aware of that and go watch that video that I have out. All right, so note number 2, which is the only location that you see a reference to note number 2, is when you see it up in the top of the table where it says secondary protection, see note 2. This is just to remind you, and I'll read it and then I'll bring context to it. It says, where secondary overcurrent protection is required. Okay, so where it's required because you're going above the 125% for the primary only protection, and now you're going to have the secondary protection. Here's what it says. It says, the secondary overcurrent device shall be permitted to consist of not more than 6 circuit breakers or 6 sets of fuses grouped in one location. It says where multiple overcurrent devices are utilized, the total of all the devices' ratings shall not exceed the amount value of a single overcurrent device. So this allows you to have up to 6. This would allow you to add them up as long as that accumulated value does not exceed what would be required of a single overcurrent device. In this case, the maximum is still 125%. So whatever you would select at a single breaker, this allows you to do this up to 6 using kind of like the 6 disconnect rule. This would allow you to do it as long as the cumulative value of all those devices that you choose to do, 2 to 6, does not exceed the value that it would be if you chose a single device, and in this case, not to exceed 125%. You with me? So if you had 6, you're going to basically pretend like you had 1 to find what that value would be. And then I guess you could divide that by 6 and see what the maximum rating could be for 6 devices. Okay. So, I mean, that's just one way to do it, but you have to remember that that all collectively can't be more than what it would be if you were using a single device. Even though you're using 2 to 6, pretend like if you were using a single, how would you size it? And your cumulative rating cannot exceed that of a single if you were using a single. Make sense? So that's why it makes that reference, because there's many transformers where we come off of that and it could feed 2 to 6 devices. Okay? So just a note to be aware of that. All right, and then of course 3, I talked to that already, and that's just talking about the allowance to use 6 times the current rating or 4 times, depending on what the impedance is, as long as it doesn't exceed 10. You have different options there. All right, so this is overcurrent protection in its clearest, purest form. So real quick, I want to talk about some of the formulas, because I know that when I talk about podcast, and I know I'm going to go a little bit beyond this person's question, but I want to make sure I bring some of this into context for everybody, right? Just kind of, make sure that we're all on the same page, that we all are grasping the same concept, and that's what we're going to do. So I want to remind you that today's examples, or anything that I give in today's example, we're going to be basing this, especially with a conductor sizing, and I am going to throw that in because he asked about it. I want to make sure that we understand that we're going to be utilizing the givens of the 240.21 C2. And this is for secondary conductors that are not over 10 feet. Now, there's rules that apply. If it was 25-foot rule, there's rules that apply. But we have to keep it simple for this podcast. We have to keep it very simple because I don't have a visual that I can give you, right? So this is all I can do. All right, so let's go on and give you some formulas. So when we're calculating transformers, if you haven't watched my video series by now, if it's single phase, we have a formula we use to find out what the line currents would be. And it also would be the same as what we find out the secondary currents at the transformer. So we're looking at the currents of the actual transformer. And so single phase, to find the current, it's just the VA divided by the voltage. Pretty simple, straightforward. If it's 3-phase, got to remember that 3-phase is going to utilize 1.732. That is the square root of 3. We always have to assume that in our calculation, and that applies to the voltage, of course. So the VA of the transformer divided by the voltage times 1.732. Now, there's values that you can just put into your head that you can just remember. If I'm dealing with a 208-volt secondary 3-phase, then I would take 208 times 1.732, and that is 360.25. Now, people like to round, so they say, well, isn't 360.25 really 360.256, so it's 360.26? Okay, if you want to do that, it's not going to change the equation, but go for it if you feel like you need to do that. I will usually only use 360.25 and just stop at 2 decimal points after. Okay, that's just me. You do you, boo. But that's what I do. So 360.25, in fact, in many places, they just use 360 and it gets you close enough in the real world. But for exams, I like to be, as close as we can. So 360.25 is what I'd use for 208 volt three-phase. If it's 480 volt, then I'm going to do that the same way. And that's going to be 831.36. So people are conditioned to use just 831. But again, you know the formula now. Use the exacting value. So 831.36 is what I would use in this equation. And that's going to take the place. That is the new voltage value that we're going to use in our equation. Okay. So we're going to do that and give you some examples in a second. But those are your formulas. So I equals VA divided by the VA, which is the VA of the transformer, divided by the voltage of the transformer, both either primary or secondary, same thing. Okay. And then the three-phase is the same concept, except for using purely the voltage. We have to take the voltage if it's three-phase times 1.732. So we learned if it is a 480, then it's 831.36 is the value we're going to take the VA and divide it into. And if it's 208, we're going to use 360.25 as the voltage value that we divide the VA into. You with me? So that's the formulas that you're going to use. And that's going to give you the line current, and it's going to give you the values that you need to size conductors and size the overcurrent protections for these transformers. That's what it's going to get you started. Okay? Now, as we looked at table 450.3b, we have learned very quickly that this is only about the transformer. We're not talking about the conductors yet. We're not talking about primary conductors. We're not talking about secondary conductors. I'm getting redundant here, but I do that on purpose. So for all those out there that have the urge to comment and say, Paul, you're redundant, save your breath. I already know it. You're not giving me an epiphany, folks. I know it because I do this on purpose. So if you don't like it, don't watch my videos. That's all I can say to you. You're not of interest to me. Okay, go on with your life. You don't concern me. But those that want to learn, those are the people that concern me. And they're the ones that I want to help. You're a smart ass. I don't want to help you. Go out and struggle in your own world. I'm not here to help you. Okay, so that's the difference between me. I'm blunt. I'm straightforward. Okay, if you're not here to learn and you're here to be a snarky whatever and post comments, then take your ass somewhere else. That's not what I'm about. All right, so for all those that want to listen, let's go on. So we're going to size the protection. Now, I want to give you an example of an application where I would use the less than 9 amps. So, and I'm doing primary protection only. So in this case, if you see it's less than 9 amps, it's 167%. There is no rounding up. It has to be rounded down in order to provide this protection. Okay. So in this example, if I were to do, let's say, a 3 kVA load, and let's say that I'm going to size this and I need to do this, then I'm going to say, okay, well, if it's 240 volts single phase, then I'm going to do it this way. I'm going to go 3,000 VA divided by, because it's single phase, right? 3,000 VA divided by 240. That's 12.5 amperes, right? So that is my primary current, 12.5 amperes. Now, I have to take that and say, okay, that value, 12.5 amperes, that is over 9 amperes, right? So you're sitting there going to say, well, that's over 9 amperes, so it says current's less than 9. So that's going to kick me into the 9 or more. But what if it's a smaller transformer, and that's what this intent is? What if it's a 2 kVA transformer? Well, let's do that and see. So a 2 kVA transformer would be 2,000 divided by 240. Much smaller transformer, that's 8.33 amperes. That is my primary current. Well, in that case, it would fall under the 9 or less. Or less than 9, I should say. Less than 9. Not 9, but less than 9. Okay. If that's the case, then under 450.3b, we would apply 167%, and that is a maximum value. Okay? I could not go up. I have to, that's a maximum. I don't have any little note there. That's it. And the table's rated maximum. So that'd be 8.33 times 1.67, and that is 13.916, which will round to 13.92, and I have to protect that transformer, and I can't exceed 13.92. So chances are with that, I'm going to have some type of fused protection in order to be able to achieve this. Okay. Now, moving on, let's talk about the more common application, and we're talking about primary protection here, is where I'm going to have the protection for a 45 kW transformer. These are very common sizes, 45, a 50, 75, 25. These are very common transformer sizes. And this rule, this lesson is going to apply to all of those. Doesn't matter. Same concept. We're using the VA value of that transformer to work it. So it doesn't really matter. Just know that 45 kVA is 45,000 VA, a 75 kVA is 75,000, a 25 kVA is 25,000. You plug it in the same way. It's the same math either way. But in this case, we already know that our value, current rating, our value is going to be greater. It's going to be 9 amps or greater. We already know that. Just looking at this, we know that. We just did one, and it was at 3,000, it was greater than 9. So we get this. So we know what the maximum is going to be, and that's going to be 125%. That is the maximum. So if I'm asked what is the maximum primary protection over current rating for that 45 kW transformer, then I'm going to be doing what is the max based on this table. And remembering, it's got nothing to do with the conductors yet. This is just for the transformer protection. Maximum, 125, okay? So if this is the case, then we do our math again, and let's just give you the lay of the land. We're talking about a 480 volt transformer. It's 3-phase, it's 45 kVA, and we're going to calculate that out. So 45,000 divided by, and what did we say earlier? Since it's 480, we said that we would be using what? Well, you can do it. It's pretty simple. 480 times 1.732. That is 831.36. So that's the value we're going to use. So 45,000, using our formula that we talked about earlier, divide that by 831.36. And that equals 54.128. So basically, it's 54. We drop the 0.12. Okay, major fraction, 0.5 or greater, you round up. Less than that, you drop. So it's 54 amps. Now, we're doing protection, right? So then we go back and look at the code, the table, and it says, okay, well, that falls under that 54 amps. That's obviously 9 or more. So that says primary only protection, we're going to go up to 125%. Okay? Okay, well, we do that. So let's take that 54 times 1.25, and that is 67.5, correct? Or since it's 0.5, we're going to round that up to 68, okay? Now, the first thing that you have to remember is we're talking overcurrent protection now. I have a value now. I did the math. The maximum is 125%. So now I'm going to go in 240.6a and see if there's an overcurrent device that's exactly rated for 68 amps. And in doing so, you'll notice that there is not. So that note 1, which is so important in the table, allows me to say, you know what, that doesn't correspond. And we're talking about the 125 value, and not talking about the 250. We're talking about the 125 value, and this is where the note is. I'll go on and let you go up to the next standard size. That's fine. So you went from, it's 68 amps, but I can put it on a 70 amp overcurrent protected device. And due to the notes, due to the way it's written, I'm okay. I'm perfectly fine. And it's considered protected. So that's our primary side. We haven't even talked about secondaries. We haven't done any of that. In fact, this episode is not even talking about secondary conductor sizing. That's in my series that we have on transformers. But I'm going to give you some context anyway, but just kind of talking you through it. Now, remember that table, 450.3b? If I did not exceed 125% primary, then I don't need any protection for the secondary winding of the transformer. However, I do have secondary conductors, and I have to meet those secondary conductor rules. In this case, if it's a 10-foot tap rule, I have to meet the secondary conductor rules of 240.21c2. And it has where that secondary conductors are sized not less than the calculated load on the circuit supplied by those secondaries. So whatever the load is for that panel, they can't be less than that, whatever that load is. And then it also says, well, I also have to consider that those conductors cannot be less than the rating of the equipment containing conductors or not less than the rating of the overcurrent protected device at the termination of secondary conductors, right? So whatever they terminate into, whatever the rating is of whatever they terminate into, whether it's the device or into a cabinet or into an overcurrent device, those conductors have to be equal to or greater, sizing-wise, straight out. Easy. 10-foot 10-foot secondary rules, easy peasy. And that is mostly what you deal with. Because most of the time, your transformer is the primary, which doesn't have a length requirement on it, be honest with you. Doesn't say where that overcurrent protection has to be. Can run halfway through a building. But when it comes to the secondary conductors, we have length limitations that we have to worry about. And the whole concept here is we're connecting to the secondary and we don't have any protection of those conductors at that secondary connection point. So we're going to limit you the length. And then they got to terminate into a device that is going to be load limiting, or it's going to terminate into an overcurrent device that has a rating that those conductors have to be equal to or greater in capacity than whatever it terminates into. You with me? So that kind of takes care of itself, to be honest with you, especially in this 10-foot secondary rule. Okay. Now, I will tell you, we have other rules here for those secondary conductors. Go watch that video series. You'll learn all you want to know about it. So I can't obviously go into all that in a podcast. I know you want me to, but I can't. I just can't. There's no way we can convey it all on an audio wise than we do visually showing you. So check those out. All right, so now let's look at this here and do a little calculation, what we already did. So 70 amp overcurrent device is perfectly fine, utilizing 240.6a, utilizing the note 1 of 450.3b. It was 68 amps of the rating of the overcurrent device. It didn't correspond, so we moved up to 70. Perfectly done. Fine. Everything's good. So now for craps and giggles, I've kind of answered the question for the gentleman, but let's go on and see, well, what happened? How do we size those primary conductors for this example that I just gave you? All right, fairly straightforward. Now, the first thing is you have to know what those primary conductors are going to see, if you will, right? So they have to understand that there's a requirements for 210.19a1 that tells us that we take for conductors, we're sizing based on 125% of any continuous load and 100% of any non-continuous load. Now, this is going to assume that you've already done the loads that you need to do at the panel that's being supplied by this transformer. And you've already taken your loads into consideration, your continuous loads and your non-continuous loads. And you took that in consideration when you sized that panel, right? You need that information because when you're doing the primary conductors, you need to take that in consideration because they have to be at least sized to handle 125% of continuous and 100% of the non-continuous. Now, I'm going to give you a little tip. This is not exam prep. This is just a tip. If there is any continuous loads taken into consideration in the panel that's being supplied by this transformer, make it easy on yourself. And again, this is not exam prep. I'm just telling you, because in an exam, they'll tell you whether to consider these as continuous or not. I'm saying in real world, it's so much easier for you to just take those conductors that are on the primary of that transformer. If there are any loads in that that are going to be supplied by that transformer that are going to be rated as continuous loads, and you liable to have them, whether it's the lighting loads, maybe it's a commercial building and you've got some lighting loads that are being supplied by the, okay, so if they're continuous loads and the code dictates they're continuous loads, then the easiest thing that you can do personally, make life simple for you, is size it as its continuously loaded transformer. So just take the values of that transformer line current at 125% and size the conductors accordingly. I'm just saying, make your life easy. So if we're sizing those primary conductors and we have that consideration, and let's just say that their conductors have to be sized for 125% of the continuous load, 100% for the non-continuous load, And you also got to remember that you have terminal limitations at 110.14. So we got to take those into consideration. Okay, 100 amps or less, then we're going to be at 75 degrees C unless all the terminals are rated for a higher value and the insulated on the conductors are rated for higher. But if we don't know any different, then we're going to be 60 degree, right? If we're over 100, then we're going to be in 110.14 C1B. We're going to be dealing at 75 degrees. So these are just things that you got to take into consideration, okay? If I have any adjustment or corrections that take place, then I have to take those and apply the adjustment and corrections, 310.15B1 or 310.15C1 for the condition that I'm dealing with. And I got to make sure that I have a conductor that can handle the ampacity after any adjustment or correction. Okay? And I'm going to tell you, that value is going to be, at minimum, it's going to be the line side current of the transformer after any adjustment and corrections. And that's typically what most people will do in that scenario, right? So again, taking all those things into consideration, now we can fully look at what we're dealing with. So let's go on and size this example and take what we have. I'll also remind you that when it comes to conductors, again, that you do get to utilize the allowances in 240.4, which is B, which says if it's not exceeding 800 amperes, then we'll let you go up to the next standard size overcurrent device, and it's still considered to be protected. And you're familiar with that. We do that all the time in conductors and things like that when we're protecting conductors, the next size up rule. Again, there's little nuances in 240.4b that you have to be aware of, but in general, you're all probably familiar with that next size up rule when it comes to that. Okay. Now just remember the 240.4b does not apply to secondary conductors. Does apply to primary. Okay. And you say, well, where does it say that, Paul? Well, you got to read the language in 240.21c and B, for that matter, will tell you that. Okay. So I'm not making that up. That is there. Go read it. You'll see that language. It'll exclude the use of 240.4b in these applications. Okay. Now, primary conductor sizing. Let's go on and do this. So we already know what's a given. We said it was a 45 kVA transformer. I'm going to tell you that it's, I'm going to use my rule of thumb, is I'm going to treat it as continuous loads only, and I'm going to take the full value as a continuous load. And it might be somewhere lesser than that, because you remember, we're sizing that transformer based on whatever we calculated the loads were for that panel anyway, and then we selected the transformer. So in doing so, we kind of know that transformer should be sized right, and we're going to assume this 45 kVA was sized right to handle the panel that's on the secondary side based on a calculation of all continuous loads and non-continuous loads. So we're going to assume it's sized right. But because of that, we're going to say that this is what's called a continuously loaded at some point transformer. And to make it easy on me and you, we're going to say that we just treat it as continuous loads. Okay? All right, so in sizing, we're going to take that 45,000 VA, and remember what we did earlier? In fact, you don't even have to redo the math. We know that it is, for the primary, it's 480 volts, it's three-phase, so we know what we're going to use, right? You should know by now what we're going to use. We're going to use 831.36 as our value, and that is basically 480 times 1.732. So we're already going to do that. So we've kind of already done it, and that was 45,000 VA divided by 831.36, and that is 54. Now, we're taking these conductors now. We're sizing conductors. We've already done the overcurrent device. That was a 70 amp. We did that. That was for protecting the transformer primary. Now, we want to see if that's still good enough to protect our conductors, because that's important. Okay? So that is 54 times 1.25. That's 68 amperes. Now I have to have a conductor, okay, that can handle 68 amperes. So I'm going to go to 310/16, and I'm going to see what conductor I would need. Now, again, we're going to I will tell you that I didn't tell you any values. I didn't tell you insulation values. I didn't tell you terminal values. I didn't tell you any of that, right? So you're going to go to the 60-degree column because it is less than 100 amperes. It's 68 amperes. And we need a conductor that can handle it. So we're going to go into 60. Now, if the terminals were rated 75 and the conductor's insulation is rated 75 or greater, then I could go to the 75. But in this question, I didn't tell you any of that. And so that's why 110.14 comes into play. And in our case, 110.14C1A1 is going to be the driver here because I don't have any variables. So if I go to 310.16 and I go to the 60-degree column, I'm going to go down and I need a conductor that can handle 68 amps. Well, it looks like a 6-gauge only handles 55, but a 4-gauge copper handles 70. And remember, assume copper unless stated otherwise. 70 amps. Now, can a 70 amp conductor handle 68 amps? That we've already calculated everything out with the continuous loads, and we've already done it. The answer to that is absolutely yes, it can. So right now, 4-gauge looks like it's the winner. The next thing that we have to determine is, okay, I picked my conductor. I get it. Is my conductor going to be protected at its ampacity? Well, the short answer is absolutely. The long answer is, well, I got to go look and see what 240.4 says. In this case, a 4-gauge conductor that's rated at 70 amps at 6 degrees C is being protected by a what? A 70 amp primary overcurrent protected device. So that primary protection that's protecting the transformer primary, and in our case, it's protecting the transformer primary and secondary because we didn't exceed 125%. It is also protecting that primary conductor because the 4-gauge is good for 70 amps and I'm terminating on a 70 amp overcurrent device. So everything's good. That one device can serve double duty, if you will. It's all good. Done. Makes sense? So that's just that simple in how you would do this. The only thing that makes these complicated is when people start throwing the what ifs in there, the what ifs. Well, if you want to throw what ifs in there, then you make sure you plug the numbers in the same way we did this one, and it's still going to work out the same. Okay? Still going to work out the same. If the current was over 100, then we're going to use the values from the 75-degree column because of the rules or the language that tells me in 110.14 C1B. Okay? Just that simple. Now, for craps and giggles, we'll go on and size the secondary conductors since we already covered the primary protection of the transformer and it covers the secondary transformer already because we didn't exceed 125. We size the conductors for this 45 kVA transformer. We size the primary, and those conductors are protected. We established that. Now, what about these secondary conductors? What are we going to do for those? Okay, so in our case, we're going to make sure that we're at 240.21, and we're going to be at C2, because I said in our examples, we're going to use the 10-foot secondary conductor rule, so not exceeding 10 feet. And we're going to follow these rules. And we're going to have to make some assumptions here, because one we know, but the others we don't, so we're just trying to do the basics here. All right, so the ampacity of those conductors, if you look at 240.21 C2, I'm going to read it to you. And we're going to kind of do a little bit here with this. It says, transformer secondary conductors not over 10 feet long. It says, if the length of the secondary conductors does not exceed 10 feet, and that is 10 feet from the point that it leaves the transformer up to the termination into the overcurrent device, let's say in a panel, or to a piece of equipment that has the ratings on that, the amp ratings on that equipment, then I'm going to follow these rules for the conductor sizes. And here's what it says. Number one, this is the ampacity of the secondary conductor rules. It says, those secondary conductors for this 45 kW transformer, A says, not less than the combined calculated load on the circuits supplied by the secondary conductors. So that means that you had to do a load calc, which you should have done anyway. And that's what drove you to size the panel anyway. So you had to do a load calc. Okay, so the first thing is those conductors cannot be less than to handle that calculated load. And that would be any of those loads you did at 125% for continuous and 100% for non-continuous. So you have a load value. So you got to do a load calc at the panel if that's what you're supplying, a panel. It says, and not less than the rating of the equipment containing an overcurrent device supplied by the secondary conductors. Okay, so that means if I have a panel and I have an overcurrent device, which is required to protect that panel guts, we call the panel board, The cabinet is what the panel board goes into, and we have a breaker in there. That is protecting the panel board, okay? And it falls under the rules of 408. But here it's saying it can't be less than the rating of the equipment that's containing the overcurrent devices supplied by the secondary conductors. So what if you had a piece of equipment and it has overcurrent in it, then what it's saying is that the rating of the equipment containing the overcurrent device supplied by the secondary, so it can't be less than whatever that's rated. So in theory, if I have an overcurrent device and they're rated 200 amps, then the equipment will be rated for 200 amps. Okay, so I can't exceed the rating of the equipment, whatever its rating is. And it says, or not less than the rating of the overcurrent protected device at the termination of the secondary conductors. So where typically what happens is when I come in from those secondary conductors, if I'm going into a panel, I'm going to go straight into that overcurrent device. And that is going to protect the panel board under the panel board protection rules. Okay. So if that's a 200 amp panel on that secondary, then those secondary conductors have to be equal to or greater than the rating of the equipment that contains overcurrent devices, or the rating or equal to or greater than the rating of the overcurrent device to which they terminate into under this 10-foot secondary rule. Okay. Can they be larger? Absolutely. But they have to be equal to or greater in size to handle that current. All right. So if we kind of got that out of the way, in our case, again, we're going to assume the same way we did on the primary. Since we did that for the primary, we're going to assume that this panel does have continuous loads in it. And rather than just dissect it out, the worst case scenario is just take the entire load or take the entire secondary, since you've already sized that transformer anyway, to make sure that that secondary current, rated current of that transformer can handle the load that you calculated. We're just going to keep it simple. We're going to, again, you're paying for a transformer, so you might as well take the value of the transformer's rating. Now, some of you say, well, I don't need to. You can do less. Absolutely. As long as those conductors can handle the load that's in that panel or the rating of the equipment that contains overcurrent devices, as long as it's sized to that, it could be sized just to handle that and you're good. But we're going to take the actual rating of the transformer secondary, which we've already, we got to calculate out, and that's what we're going to utilize. So let's work this out. So we're going to determine, we're just going to make it simple on us, and we're going to treat this as just take the full value as a continuous load and just work it that way. Again, real world, remember, those conductors can handle 125 of continuous, 100 of non. If there's any continuous loads and you don't want to go through the math, just do it at 125% of the rating of the transformer and secondary, and you're going to be fine. Okay. Again, this is not necessarily exam prep, but real world. So first thing is we have to determine the rating of the device that is supplied by the secondary conductors and at 125% of the secondary rating. Okay. So 215.2 A1A. Again, if there's any continuous loads, we do that at 125%. Again, of continuous, 100% of non. So we're establishing that, and we already told you there's some continuous loads in there. Maybe it's for lighting, so we're already going to go there. And so for us, we're just going to use the rating of the transformer. Second one, it says size of transformer conductors so they have an ampacity, at least the device rated being supplied by those secondary conductors. And that's what it said in 240.21C2. Now, you obviously are going to size them to handle the calculated load, but I think more importantly is the rule that says, okay, well, it can't be less than whatever the device is, or it can't be less than the overcurrent device that you're terminating into. I think that's the more important of the rule, to be honest with you, right? So if we have that 45 kVA, and we're going to do it as continuous loads to keep it simple, we have 40 volt primary, 122.08 volt secondary. We need to determine what the secondary current rating is. Just like we did before, it's 45,000 VA. Divide that by, and what was the value we're going to use? 360.25. Why? Because that's the square root of 3. And we're going to take that value and multiply by 208 volts because it is three-phase. And that ends up being 125 amps. Okay? So you can verify that out. But let's just do it on a calculator if you're following along. 208 times 1.732. That is 360.256. I'm only going to go 2 points out, so it's 360.25. But if you want to go to 360.26, it's not going to change the equation. That's totally, if you want to say, what, Paul? We got a round. Okay, you do that, boo. It's not going to change it, but go ahead. All right, so that's what we've got. But I'd at least go out 2 spots if available. So in that case, that's where we get that. So we divided the 45,000 divided by 360.25. And that is 124.9. Obviously, 0.9 is a major fraction or greater. We get those rules in 220.5. So it's 125. Now, once we have that current rating, remember we said we're going to take these and we're going to size these conductors and we're going to treat it as continuous load. Remember, we're doing conductors now. And it's going to terminate into an overcurrent protected device. But since we have to size these conductors and it can't be less than what the device is going to be, so we're going to choose what that device is or what it has to be for these conductors. So I'm going to take that 125 amps, multiply that by 1.25. And that is 156.25. Now I can drop the 0.25. Now, these conductors safely can terminate, and we don't know the size yet, but we know that this conductors, when it comes to the ampacity value, it can safely terminate into a device that is, again, we're talking about the overcurrent device, at 175 amps. Okay, that's the device. Okay, we're taking it secondary. Now, we're going to, since it doesn't correspond to 156, then we're going to have to use the next size up, which is 175 amperes. Now remember, we're not upsizing the conductors. We're selecting the device that they're going to terminate into. Okay? We haven't picked a conductor yet. We're just doing amps. We're just sizing the overcurrent that's going to be terminating it. Now, one thing that people get confused is that you got to remember, this is based on the transformer's secondary rating. So that panel, regardless of what you want to say, well, at the panel size based on my calculated load, I get it. But the transformer secondary can only handle so much. So by doing this, we know what the maximum that would be as an overcurrent protection in that panel that these secondary conductors are supplying. And hopefully that does handle the load. But this is the value, the maximum it can handle based on the values that we have here for continuous load. Okay, don't let it confuse you. We're sizing now the overcurrent that these conductors are going to turn into or connect into. Now, one thing to remember is we might size the panel and the main breaker based on whatever our calculated load was, and that might end up being 175. All we're saying is based on the secondary of the transformer and taking it at 125%, which is the maximum that we can have for secondary protection of a transformer, which we weren't required to have. But when it comes to these conductors, we have to treat the conductors as, in this case, handle continuously loaded. They're continuously loaded. So that's why we went from 125 amps times 1.25 at 156. It doesn't correspond, and we're sizing overcurrent protection that these conductors are going to terminate into. Since it does not correspond, then we're able to go up to the next size, which is 175. Now you're saying, but Paul, you told me I can't go up. I can't go up in size. I can't jump up. You can't. Now and only then are we going to size the conductors now. We know what they're terminating into. We know what the current is of the secondary of the transformer. We know the rating of the device it's connecting into, which is 175 amps. Now, what does it say under 240.21C2? It says, and that would be C21B, it says the conductors not less than the rating of the equipment containing an overcurrent device. So again, it might be a piece of equipment that has a device in it, an overcurrent device in it, or not less than the rating of the overcurrent protective device at the termination of those secondaries. In this case, it would be a 175 amp overcurrent device. If that's the case, I have to select a conductor that can handle that value, 175 amps. So then I'm going to go back to 310.16, And now I can use the 75-degree column, even if I haven't been given any insulation types or whatnot, because of 110.14C1B, since we're over 100 amps, then it says I can use the 75-degree. So I'm going to go into the code book, and I'm going to go under the 75-degree column, and I'm going to go down, and I need a conductor that can handle 175 amps. So if I go down this list, I notice that, well, a 1-augh's not going to work. That's only good for 150. That a 175 for a 2-aught is what I'm going to need. So because that overcurrent device in that panel was 175, let's say just the main breaker in that panel that's there to protect that panel board and hopefully sized adequate to handle whatever the calculated load was. But that's also the maximum that you can have based on using the values that are from the transformer. So what we did is now we are able to say, well, those secondary conductors can't be smaller than a 2-aught copper, because we assume copper unless stated otherwise. So that's following all the rules. Okay? So that 2-aught is equal to or greater than the value of the device that it terminates into. And so I can't use any next size up rule for that. In other words, I couldn't use, this is just craps and giggles, I couldn't use some value less than that and say, well, I can use an next size up rule because it doesn't correspond. You know, you can't do that here. And it tells you that in 240.21c. It says you can't do it. So that's how we size this. Now let me give you some thoughts and we'll end this one up. Most of the time, I showed you how we would do it with the transformer, and we always want to size to the ratings of the transformer. In the real world, if I want to have a panel and it's going to be supplied from a transformer, what I probably do is I calculate all my loads, right? And I calculate all my loads, and then I size my panel. And if it's a 200 amp rated panel, and I've got a 200 amp rated overcurrent device. Now, the first thing I want to do is make sure that if that's my calculated load, it might be somewhat less than 200 amps or whatever the calculated load is. I need to make sure, for one, that my transformer can handle that load. So I have to pick my kVA transformer accordingly to make sure that the secondary rating, and usually the primary will take care of itself, but the secondary output or current rating of that transformer has to be able to handle the loads associated with it. Right? So if I do that, then if it's set in stone that I have a certain value and I put my protection in my panel at 200 amperes, then my secondary conductors can't be less than what would be equal to or greater than 200 ampere rated. It couldn't be less because of the rules for those secondary conductors, okay, in 240.21c2, if we're doing the 10-foot secondary rule. So it can't be less. We already got that. So I have to look at my transformer and determine, one, whether or not I can handle that type of thing. And then I use that value and I do my calculation to size everything. But at the end of the day, as long as my transformer can handle that load, then we're okay. And as long as my secondary conductors are size equal to or greater than the rating of the device that it terminates into, and as long as the transformer can at least handle whatever the load is we calculated, then I'm okay. Then I'm perfectly fine in my calculation. So most people work it the other way. You could select the transformer, then do the math and see what the current rating is of it, and then have that say, okay, here's a 75 kVA. I think that's what I've got. In fact, if I looked at a 75, which is the most common, I go, okay, what's the maximum size that I can handle from that transformer? Okay, because the rating is the rating. So if it's 75,000 and it's a 12208 secondary 3-phase, then it's 75,000, and I'm going to divide that by 360.25, and that is 208.18. Get rid of the 0.18, so it's 208. So typically, I would say the maximum size panel on that secondary is 200 amps. Maximum size. Because the secondary current is 200 amps, 208 amps, but I'm not going to do 208. So now, Could it be somewhere less than that? Absolutely. Could I have multiple panels on a secondary that cumulatively are less than what the current rating is of the transformer secondary? Absolutely. But I do need to know that the fact that if it's a 75 kVA transformer, the maximum current that transformer can put out is 208.18 amps. So I need to make sure that my calculated load, I need to make sure that all of that for the panel that's going to be supplied, let's say, from that secondary, I have to make sure I take all that in consideration because this transformer can only handle a certain amount. Otherwise, you're going to bog it down, you're going to overload it, and it's going to overheat and prematurely fail. So it really doesn't matter which way in the real world you tackle it. You just have to make sure the transformer can handle the load. So you got to do your load calc first, size your panel. If you size it as a 200 amp panel and you're good to go, then you can go and do your transformer calculation to make sure that the current rating of your transformer secondary can easily, adequately handle that panel rating. And then make sure your secondary conductors are equal to or greater than whatever the rating is of the device that it terminates into. And you're good to go. And so most people won't even worry about all this. Most people will just say, hey, 75 kVA transformer, 120, 208 volt secondary. I know 208 is the maximum that this transformer could put out. So I'm going to put a 200 amp panel knowing that my calculated load on this panel from the secondary is going to be south of 200 amps. It might be calculated load, might be 150 or 165 or 102 or 90 or whatever. So typically they will size it because, we want to get our bang for our buck. I want to get all I can get out of this transformer or potentially. So that's how they would do it. Okay? Makes sense? So I kind of gave you all ways that somebody looking at it, designing it, would look at it. Really not an episode for exam prep, although on exam, you always go to the maximums. So in exams, I would go 125% primary and things like that. And on the secondary, do the secondary conductors based on the size of whatever the overcurrent device it terminates into. Do it that way. Follow the maximums that are written in the table because that's probably what they're going to ask you on an exam. What's the maximum this? What's the maximum that? Remembering that you can always be less than that. I don't have to do up to 125% on a primary. I can do 110%. I can do 100%. I can do 120%. But the 125 is the max. Okay? And the note just allows you to go up to the next size if it doesn't correspond. You don't get to do that at the 250 if you have primary and secondary protection. Okay? So hopefully I covered all that. Again, if it's a rambling for you and you were like, dude, I don't understand what you're saying, I'm sorry. Did my best. And if you didn't get it, I'm sorry. There's many other educators out there who's willing to teach you. Doesn't have to be me. So until next time, folks, stay safe. God bless. And hopefully I answered this one a little bit long, but I wanted to cover all the variables, kind of keep it simple, stupid. Obviously, disclaimer, I did not talk about all of the scenarios that could take place. Just trying to keep it basic. Until next time, stay safe. God bless.